let's get back to it. So I'm not sure exactly where I left off, but I'll say again that what this example sample mean A is telling us is the probability of Dr. Meyer obtaining the sample mean he obtained, if the hypothesis is true, is really small. Therefore, we're going to conclude that his hypothesis is probably not true. Remember, his hypothesis said that homeschooled students are the same as public school students. So it's this idea of indirect proof. So we're not ever going to definitively say homeschooled students are have a different mean than public school students, but we can say the probability he would have gotten the sample mean he got, if the hypothesis is true, is really small. Therefore, we're going to conclude that the hypothesis is not true, that homeschooled students do not have the same mean as public school students. Okay, so that's what we mean by indirect proof. So, how do we know for sure? What I mean by that is 2.3%. And remember, that's just a number I made up based on the fact that it's way over here in the tail. We're going to get to his actual result in a minute. But I was saying a second ago that the probability he would have gotten the sample mean he got is really small. It's 2.3%. So I'm going to conclude that this hypothesis is not true. Well, how small is small enough? How small does this probability have to be in order for me to conclude that this is not true? You see what I mean? So how do we know for sure? Well, statistical significance testing provides an established criteria for us so that I don't just have to say, hey, it's really, really tiny. I can say the probability is very small. In fact, it's below our threshold, or it's below our established criteria. So we have this criteria so that we can say, oh, okay, it's different enough, or it's small enough that the differences are not just due to chance or to sampling variation. Okay, so let's get back to what Dr. Meyer is hypothesizing. So he is saying that the mean of homeschooled students is also 250. Okay, because it's phrased as basically it's the same, there's no difference, we're calling this the null hypothesis. That's why sometimes tests of significance are called null hypothesis significance testing. So when we're talking about the z-test, t-test, ANOVA, multiple regression, whatever we're talking about, when this type of comparison or probability test is made, we're always testing the null. And the null always says there are no differences, or there's no relationship, or the intervention has no effect. So the null always means nothing. Nothing's happening. Nothing's going on. Okay? It's central in statistical significance testing. It's always assumed true, and that's what we formally test. So we are always testing the null. Even if the null is never explicitly stated anywhere in a study, we know that that is what is being tested because that's the type of test we're doing, null hypothesis significance testing. Okay? But a researcher, such as yourself, can have an alternative hypothesis, and it's noted by H sub 1. That hypothesis can be directional or non-directional. So if it's directional, that means you have an idea of the direction in which the difference will be. So he could have said the mean of the population of homeschooled students is going to be less than 250. Or they're actually doing worse than the public school students. Or the opposite. His alternative hypothesis could have said, oh no, homeschool students are doing better. It's going to be greater than 250. That would be directional. Or he could just say, you know what, I think they're performing differently from public school students, but I really don't know what direction that's going to be in. They could be doing better, they could be doing worse. And so it doesn't have a specific direction. It just says, there'll be differences, but I don't know what direction. Okay. So we're always testing the null, but the researcher can have this alternative hypothesis. Okay. So both a null and alternative hypotheses are statements about the population parameters, not the sample. And I will guarantee you that most research articles you read have forgotten this. They are talking in terms of the sample. Okay, so just kind of keep it in the back of your mind that we're actually talking about the population parameters. And of course, just like we teach our kids, starting with those first science fair projects, all hypotheses are stated before the sample data are examined. Right? You're going to state what you think is going to happen before you do your testing. Okay? So back to Dr. Meyer. Remember, his sample mean, or no, I didn't tell you this yet, but so he pulled his sample of 25, gave them an achievement test, found their mean to be 272. Okay? So how likely is this sample mean assuming the population mean is 250? Or what's the probability of obtaining this sample mean assuming the population mean is 250, or assuming his hypothesis is true? So he can do a z-test. Now, this is the only test that we'll do by hand because, again, it's just about getting the process down. After this test, we're going to do everything on SPSS. Okay, but having an understanding of how it works, you can definitely apply it to the other tests. It's just the formulas get more complicated, and that's why we use the SPSS. So the formula to conduct a z-test looks very much like when we converted to z-scores, right? So it's the sample mean, so that would be his 272, minus the hypothesized mean, which is what? 250, divided by the standard error. And we calculated that earlier, didn't we, to be 10, because we need it for this formula. All right, so let's look at it here, where I've worked it out. So 272 minus 250 divided by 10 comes out to be 2.2. So that's a z-value of 2.2. Okay? So if he has a one-tailed test, we can look up the area beyond the z and find it to be 0.0139. All right? So I want to relate this to what we were doing before. All right? So remember, earlier this semester, we were identifying where our score fell and looking up that value in the back of the book. Okay, so remember, z-scores always have a mean of 0 and a standard deviation of 1. So we got 1, 2. And so 2.2 is going to be about right there, isn't it? I think it's going to disappear. Yep. All right, that value is going to be about pretty close to 2. So it's going to be like right there. So what we're going to be looking for is this area. So we will go to our book, to our table, and find the area beyond the z. So 2.2, this area, and I went and looked it up for you, is that 0.139. All right. So the probability he would have gotten the sample mean he got if the hypothesis is true, that's a 1.3 by the way, is this 0.0139. Okay, now this is for a one-tailed test. If he thinks that the population mean of fourth grade homeschooled students is greater than 250, this is it. This is all we care about. But if he had a non-directional hypothesis where he said, you know what, it's not equal to 250, but I don't really know what direction it's going to be in, we have to think about our z value and then 2.2 is like right here. We have to think about it in terms of both tails because we're talking about probability in either direction. So we also have the 0.0139 on this side. And so like you can see here, what we do is we add those two together. And so this is what we call a two-tailed test because we're looking in both tails. This up here is a one-tailed test because we only care about this one side. But this is a two-tailed test. When we add them together, we of course get this value. So this is, if we were converting it, 2.78%. Right? So the probability he would have gotten the sample mean he got, which was 272, right? If the hypothesis is true, is 2.78. Well, that's not very likely, is it? So it's not very likely and that he would have gotten the sample mean he got if the hypothesis is true. Therefore, we can conclude the hypothesis is probably not true. But we're still faced with that idea of how small is small enough. All right, so that kind of brings us back to that criteria I was talking about earlier. Here we continue here for a two-tailed test of probability. So this is what I actually said. How low a probability is enough? So Dr. Meyer needs an established criteria by which to compare his obtained probability. So in social science research, we have what we call this alpha level. And it is our criteria, or you can think of it kind of as a cutoff value. We are going to name this cutoff value or this criteria as 0.05. So what we're saying is there is a less than 5% chance that the sample mean would have been obtained given the null is exactly true. All right, so what we're going to do then is take the one-tailed test and then we'll look at the two-tailed test and see how it compares. So in this one, remember the one-tailed test, Dr. Meyer was only looking over here and he found that probability by looking up in the back of his book, and we're going to compare that to 0.05. So if this is our critical value or our cutoff or our criteria, we're going to look for anything further out in the tail than 0.05 or any probability less than 0.05. If we find that our probability is further out in the tail than our cutoff point, we're going to say we have statistical significance. Okay, let's look at it in a two-tailed test. In a two-tailed test, we'll take our 0.05 and we're going to split it. We'll put 0.025 over here and 0.025 over here. And so we're going to compare what it is he got to 0.025. But if you look, the 0.0139 is still further out in the tail than either of those. Now, to me, this is confusing. So what I always do, and I encourage students to do, is to always use a two-tailed test, because in SPSS, what the computer does for us, that we're seeing kind of the inner workings of it right now, but it's going to give you, the computer, SPSS is going to give you a p-value or a probability. So remember, I'm going to see if I can scroll back up here. So remember this, I had to look this up in the back of the book, right? Well, when we are talking about and using SPSS, instead of us having to look it up in the back of the book, SPSS is going to give it to us, which is going to make our life a little bit simpler. So whatever the value SPSS gives to us, and they're actually going to put it in a column and call it significance or sig. Say they give you a value of 0.025. 0.04. Well, before that's given to us, they have considered it on both ends. Okay, so if it was 0.02 on both ends, then they're going to give you that value of 0.04. So you're not going to have to worry about splitting these values like this. You're not even going to have to remember that because SPSS has already doubled it for you. So whatever probability SPSS gives you, you can take it directly, 0.04, 0.05, and compare it. Can do like we did in first grade. We can compare it to determine whether or not we have statistical significance. So anything less than 0.05, any probability less than our cutoff value probability or our alpha level is going to be considered statistically significant. And what I mean by that is the probability we would have gotten the sample mean we got if the null is true is tiny. In fact, it's so tiny that it's less than our established cutoff value. Therefore, I'm going to conclude that the null is probably not true, and I'm going to reject the null. If I reject the null, we're going to say we do have statistical significance. So the population mean of homeschooled students is statistically significantly different from the population mean of our general ed students. Okay, now that's kind of wordy and kind of convoluted. It's that indirect proof, but you're going to get the hang of it. Okay, we have a couple of different types of errors. Wouldn't you know it? We can always make a mistake, right? We can have such a fluky sample that it messes with our results. Okay, so think about Dr. Meyer. What if Dr. Meyer, unknown to him, pulled a sample of 25 GT homeschooled students? And that's why they got a mean of 272. Not that the general homeschooled mean is actually different from 250. It's just that his sample was kooky, right? We wouldn't know that necessarily at first. Now, if we replicated the study, we'd figure that out. Or if someone came behind us and replicated, they would figure it out. If we make that mistake, if we say there is significance, if we reject that null when in fact the null is actually true, then we've committed a type 1 error. Okay? If we do the opposite, if Dr. Meyer made another sampling goof, unknown to him again, what if he pulled a sample of 25 homeschooled students who had been transitioned to homeschooling because they were failing and their parents wanted them out of the public school? I know that's a crazy example, but say for some reason his sample actually was not representative of homeschooled fourth grade students, and the mean really was, the population mean really is right around 250, then if we retain the null when in fact it's actually false, and we say there are no differences in the means when there actually are, we've committed type 2 error. Okay, so rejecting the null when we should not have is a type 1 error. Retaining the null when we should not have is type 2 error. Okay, so, but again, we're really not going to know if we made an error until we replicate or until someone else replicates, so you can get an idea of how important replication is in research, because we can't find our mistakes if nobody tries to replicate it. Okay, so when the obtained probability is lower than the alpha value of 0.05, we say the results are statistically significant. Now, in some cases, they'll lower that cutoff value or that comparison value, that critical value. It has a million names, I'm sorry, to 0.01. And that just means they want to be even more sure of their conclusion, whatever it is. So, but generally, social science, standard, and I think even medical science, and well, it depends on what you're doing. Because if we're talking about life and death, we might, if this is 1%, we might want even less than 1% assurance, right? But for us, we're saying, I'm okay with this 5% probability of making a mistake, right? So we are going to compare whatever probability we get with 0.05. And this is what you'll see in the majority of the journals. So this is just a little wording that I pulled from a dissertation probably. I wanted to point out it's revealed a non-significant main effect. So whatever their probability was, it was greater than 0.05. They didn't report their actual probability, but they did report that it was greater than 0.05. And here another non-significant effect was also greater than 0.05. Okay. Now, there is some criticism of statistical significance testing, and the article that you read by Henson really gets into this, but I want to show you mathematically why it's criticized. Okay, so think about this. As your sample size increases, as n increases in size, the denominator increases, right? As we divide by a larger number, the result is larger. Okay, so think about that. Think about a pizza. This is how I like to remember how this works. If I have a pizza, if I divide it into more slices, if I divide it into more slices, then I am going to have smaller slices, right? But I'm going to have more of them. Well, if my sample size increases, then if my sample size increases, then this is going to get what? Smaller. And if my denominator is smaller, what's going to happen to my z? It's going to get bigger. The bigger, let me show you this on a little picture here. If this is my curve, and I'm saying that in order for something to be statistically significant, that z value's got to be out here in the tail in either direction, because we're thinking absolute value, right? Well, if I can somehow get my z to be bigger, it's going to push it out in the tail, because right, a z of 0 is right here in the middle, right? So the bigger z gets in absolute value, the further out in the tail it is. So if I can increase my z, then I can almost certainly ensure that I'll have statistical significance. Because remember, my threshold is 0.05. So any probability less than this is going to be significant. So any probability less than 5% is going to be statistically significant. So if I can get my z further out in the tail, then that's going to decrease my probability. And that's what I want. I want my probability to go down so that it'll be less than this. Because if my probability is less than 0.05, then I have statistical significance. Okay? So if my sample size is larger, my answer is going to get smaller here. My standard error is going to get smaller, right? If I chop my pizza into more pieces, my slices are getting smaller, so my answer is getting smaller. My standard error is getting smaller. If my standard error is smaller, everything else remaining the same, if my standard error is smaller, then that means my z is going to get bigger. See what I mean? So if I add enough people, I can always find statistical significance. So it is widely criticized as being able to be manipulated, right? I can manipulate whether or not I find statistical significance simply by adding participants. Not always simple to add participants, but I can manipulate whether or not I find statistical significance by adding participants, okay? So it's criticized. Why are you learning it then? Well, it's a first step. The Henson article and in later this, as we progress this semester, you will begin to see kind of the next step of what we'll do. We're going to start to use statistical significance testing as almost a means to an end. So we're going to start here because it's, kind of historically the process. And then we're going to learn some pieces to add to statistical significance testing to supplement or to add more practical significance, if you want to think of it that way, and we'll get into that because we want to be aware of this criticism, but this is where we're going to start and we're going to add to it. The next slide kind of talks about that. Because of that criticism, we have started to talk about things like effect size, which is more of the practical significance. So if you want to think about it this way, statistical significance says, do differences exist? So is the homeschool mean different from the public school mean? Well, our answer to that was yes. Based on Dr. Meyer's sample, we said yes, there are differences. The practical significance, or the effect size, will tell us the magnitude of those differences. Okay, so we're definitely going to bring in effect size as almost another piece to the puzzle. Okay, so next I'm going to go through one other example of the Z-test, and then I encourage you to go back through this and check out the other example that's posted in addition to the one I'm going to make a video for, so that you can really start to get a feel for this statistical significance testing.